Welcome back. This is part 1 of the course on vectors, where I'll introduce the concept of vector for the first time and tell you about some of their potential uses. Let's begin. So, what is a vector? I find two ways of introducing them. The first is a geometric/visual way, while the second is a more mathematical/abstract approach. As you might expect, the abstract definition is more general, and the geometric approach can be seen as one particular case of the other. However, as you might also expect, the abstract concept is a bit more complicated and it's best left pending until the student has a solid understanding of the geometric visual interpretation. So let's take the first approach. A vector is a directed line segment. This blue line I drew here represents the direction the vector is facing. The white arrow itself is the vector. The beginning of the arrow is called tail, and the end is called the tip or head. So now let's break down the group of words directed line segment. The line segment part implies that it has a specific length or size. The directed part means that it follows a specific direction, and the arrow represents said direction. So, according to those two concepts, the following pairs of vectors are all different. In the first case, they have the same size, but point towards a different direction. In the second case, both vectors are in the same direction, but their sizes are not equal. Hence, they're not the same vector. These geometric vectors are heavily used in analytic geometry and classical physics. So, we already know what a vector looks like geometrically speaking, but how about mathematically? Well, it is an n-tuple, which is the mathematical way of saying list of n elements. There are different ways of writing them, but the one I'm gonna use is the column vector, which is the one I'm showing you right here. There are a few ways to write vectors in order to differentiate them from numbers, but the two I'll use are either a bold letter or a bar on top of the letter as shown here. So, if you see a variable with bold font or with a bar on top of it, you'll know it's a vector. Now, you'll notice that between the brackets there are other variables, from u1 to un. These are called the components of the vector, which are numbers. These components could belong to any of the sets of numbers we studied last episode, but typically they'll be real numbers. Please note that under the context of vectors, the numbers are called scalars. Also note that the list of numbers and the arrow represent the exact same thing. They're equivalent. Now, regarding this number n, it's a whole number and it represents the number of components the vector contains. This value is also called the dimension of the vector. Let's see a few examples. A vector of dimension 1 only has one component, and if you think about it, that's just a real number. So typically, talking about a one-dimensional vector doesn't make sense. Now, a two-dimensional vector can be represented in a two-dimensional coordinate system. For now, I'll draw the tails of the vectors at the origin, but know that this isn't always the case. A three-dimensional vector can be represented in a three-dimensional coordinate system. Notice that this vector has three components, and as the dimension grows, the number of components does as well. Only when a vector has its tail at the origin, the components tell you how many units to move along each axis in order to reach the tip. So, for the first example, you move u1 units along the only axis. For the second example, you move v1 units along the first axis, and then v2 units along the second axis, and then you reach the tip of the vector. For the third example, you move w1 units along the first axis, then w2 units along the second axis, and finally w3 units along the third axis. Now you may be wondering, how does a vector of higher dimension than 3 look like? The truth is, we don't know how to draw them. Vectors only have a geometric representation up to 3 dimensions. Beyond that, we can't draw them anymore. The best we can do is extrapolate the properties we study from one, two, or three-dimensional vectors to higher dimensions. Luckily, three dimensions are plenty for games. The games you'll design will be either two or three-dimensional, so for now limiting our study to those cases should be enough. For the last part of this video, I want to talk a bit about why vectors are useful in physics. So let me begin by saying that some physical quantities can be represented by a single number. Some examples of this include the amount of matter, aka mass. Think about it. Whenever you speak of the mass of an object, you say it's something like 80 kilograms. Another example is pressure. When you read the pressure on your cars, bikes, or whatever's tires, have you ever needed anything else other than a single number? Of course not. And the same goes for time. We rewrite seconds into years, days, hours, minutes, and whatnot, but all of that really just corresponds to a single numerical value. Now, here comes the interesting bit. There are some physical quantities that require more information. Let me give you a few examples. The car is moving at 50 kilometers per hour, but where is it heading to? A force of 50 newtons. Applied in which direction? I'm 100 kilometers away from you. Okay, but in which direction? All of those sentences are incomplete. They're ambiguous. In order to make them clear, more information is needed. Let's look at the same examples with more information available. The car is moving at 50 kilometers per hour and it's headed towards you. Move. This object weighs 50 newtons. Ah, so it's a downwards force. I'm 100 kilometers away from you. Just head north. See? When we specify not only the magnitude of the quantity, but also its direction, the sentence becomes clear, which is why these quantities are represented by vectors in physics. A simple scalar is not enough. And, what do you know? Displacement, velocity, acceleration, weight, forces are frequently used in games because we often simulate physics. So much so that all the popular game engines have their own, often complex, physics engine. Let me give you a couple of practical examples of what I'm saying. First example, your character's position in the world. To track the position of a character, we use a single point. This point often is the center of mass of whatever collider you assign to the model. Now, if we trace this rainbow vector with its tail at the world origin and its tip at the center of mass, then its components represent the coordinates at which your character is located. Or, in other words, how many units you have to move along each axis to reach the center of mass. Second example, you want to implement a jump pad. How do you do this? First, you check whether your character is standing on the pad or not. If it is, then you apply a force, aka a vector, that will yeet your character as you please. Once again, both size and direction of the vector, along with other factors like gravity and weight, will dictate where your character lands. Anyway, time for a recap of everything we studied. A vector is a directed line segment. The vector itself is represented by the arrow. Its direction is represented by the dashed line. It has a size, which is the length of the arrow. Mathematically, a vector is a list of n numbers, more formally called an n-tuple. Each of the numbers that conforms the n-tuple is called a component of the vector. A vector has n components. The value of this number n is also known as the dimension of the vector. For now, we'll focus on up to 3 dimensions, but this number can be much, much larger. A vector of up to 3 dimensions has a geometric representation, which is the arrow. For dimensions 4 and beyond, the vector no longer has a geometric representation. The best reason I can give you for studying them is that they're extremely useful in both classical physics and math. Of course, I don't need to tell you that both particularly physics, are a huge part of video games. And that's it for today. I hope you learned something and stay tuned for the next part. See you.